Okay, so we started with the linear theory. That's funny. How come this part becomes so short? Yeah, maybe I just changed it. Maybe I had to change this to introduction. Okay, anyway, we start with the linear theory. And that is similar to what we had before, except we have the y momentum equation, and then we have partial y. Okay, the rest are same as before, and also we made the assumption of the linear and implicit. There's no friction. Okay, no friction term, and Boussinesq. Okay, so we have donut here, and this is buoyancy force, and so then those equations can be combined into one equation of W, okay, or W prime. So we can, and then based on the definition of W prime, we can, replace W prime by eta, okay, in same form of the equation. So then we have this, and then once we have this, then we can make the Fourier transform, okay. And this time we don't use the one-sided Fourier transform. We just use two-sided regular Fourier transform. Okay, and the regular Fourier transform is we have eta head of KLG. Okay, we just do the Fourier transform in x and y directions. Okay. So that is equals to negative infinity to positive infinity. Okay, and then we have eta of x, y, g, and e to the I minus I k x plus ly, and then dx dy. Okay, and let me double check. Sometimes there are different forms of Fourier transforms. Okay. Oh, so here we use 1 over 4 pi square. 4 pi square. Okay. Because one transform in x, we have 1 over 2 pi, and other one we have 1 over 2 pi. So two together will give us 1 over 4 pi square. Okay. And then the inverse Fourier transform will be eta of x, y, and g equals to negative infinity to positive infinity, and then negative infinity to positive infinity. And then we have eta head of k, l, g, and e to the I kx plus ly. And then dk, dl. Okay. So then we can make the Fourier transform of this equation, on this governing equation. Okay, and that's pretty easy to do. Okay, because pretty easy to do from there. 5.4.6, and then it would become eta gg head plus m squared. Now m squared becomes different from before. Okay. So we have eta gg head plus eta head plus m square eta head. Sorry, my writing is terrible because of marker, equals to 0. Okay. And this m is pretty easy to obtain because we can easily make this Fourier transform, of del square of eta xx plus n square over u square, and there h square hat equals 0. Okay, and remember, for this is 3D. And sometimes when we derive equation, you want to see if it is. Are there any questions? You guys? Yeah. You, two of you. Yeah. You have questions? No. Okay. So it's 3D, and sometimes you want to check to see if your derivation is correct or not. And what you can do is you try to see you can reduce to 2D. Okay. So d square here is equals to partial x square, partial square, partial y square, partial g square. Okay. And there h square is equal to d square x square plus d square delta y square. Because this h means only horizontal. Apply derivatives, partial derivatives only in horizontal directions. And so once you have this, then for 2D, then this will become, okay, then this d square will reduce to d square, dg square, oh sorry, dx square. Plus d square, dg square. Okay, and then delta h square will reduce to, for 2D, okay, will reduce to partial x square. So then you substitute this back there, then we are going to have d square, dx square, and then plus d square, dg square, and then eta xx, okay, and then plus a square over u square, and then this will become just simply d square eta dx square equals 0. And now if you take the integration with respect to x twice, from negative infinity to x, then this partial x will become, then that will reduce to partial square, partial x square plus partial square, partial g square, and then eta plus a square over u square. That is the scalar parameter square, and then equals 0. Okay, and then this will be corresponding to w prime and then w prime. So then, okay, we can say the derivation is pretty okay, correct. Of course, this is only one way to check it quickly. Okay, so w prime. Okay. Okay, now, so if we have that. Then, so if we have this, okay, then as I said before, a shortcut to get the Fourier transform done is by taking partial x corresponding to ik, partial y corresponding to il, and then that will easily to reduce to that, and the next equation. Okay, so m square will be equals to k square times n square over k square over u square minus 1. Okay, and you can check it also by dating capital K square equals to small k square. That means 2D. Okay, then that will reduce to okay, the identical form as in two-dimensional problem. Okay, so we have this. Now it's almost similar to before. Okay, now you should be able to solve it easily. Why? Because the solution depends on this term, n square over k square times u square minus greater or less than 1. Okay. And so the solution also can be easily, okay, write down as the following. Okay, so we have eta hat equals to, then we have kind of we can have A e to the I mg plus B e to the I negative I mg. Okay, and M will be simply equals to square root of will be equals to kappa times n divided by square root of k square times u square minus 1, and here we have positive negative here. Okay, so n. Okay, and this term could be imaginary if m is real, okay, and would be imaginary if m is real, okay, and that gives us the vertical propagating wave. And if m is imaginary, then that become so say m is equals to in. If it's imaginary, n is real, okay, and this is imaginary. Then this become negative, okay, ng, and this plus ng, and that will require upper bounded condition, okay, upper bound conditions, which is boundedness, okay, and similar to before. So I don't think I need to repeat. Okay, you can do it at least. So depend on, okay, which case, n square over k square over u square greater than 1 or less than 1. Okay, the first one, that means the buoyancy force, because the buoyancy frequency is dominative, is larger than Ku. Ku is initial force, that is advection. And then we have the upward propagating waves. Okay, that's we call regime 1. Okay, and then n square over k square u square less than 1, that is evanescent flow, because, okay, that gives us the imaginary m. Okay, so then those terms become negative ng e to the positive ng, and this will be gone because our forcing is at the lower boundary. Okay, and the linear low boundary condition can be applied, which is eta equals to h of xy. Okay, and that's w equals to u partial. Okay, that's corresponding to, okay, 30 prime. Okay, at x, y, and 0. Okay, and that is equals to u partial h partial x plus v partial h partial y. Okay, equal to that. Okay, so now we have this. So eta, okay, solution can be obtained by taking the inverse Fourier transform. This inverse Fourier transform, we have e to the I times kx plus ly. Okay, and then okay, so we got this solution in, okay, in the physical space. Okay, and then we take the inverse Fourier transform, where negative to partial infinity, negative to partial infinity, and then h hat of kl times e to the I m g, and then e to the ikx plus ly, and then dk dl. Okay, and now h hat, okay, because of the bear shape, okay, this r square is equals to square root, r square is equals to x square plus y square. So R will be square root of x squared plus y squared. And this three-dimensional pear-shaped mountain has a very nice form of Fourier transform. Okay, the Fourier transform is proportional to e to the mass k a. Okay, see here, mass k or mass ak, and then h times a squared divided by 2 pi. Okay, and you have to be careful. A lot of people don't realize here we have 3 halves. Okay, remember in pear shape, in 2D, for pear shape mountain, okay, we have h of x equals to, anybody remember this? What's the pear shape mountain in 2D? Which hm divided by x, okay, or we can say a squared and then x squared plus a squared. Okay, or okay, h of x equals to hm divided by x over a squared plus 1. Okay, so here, remember this. So for 3D, our mountain is slightly different. It's still pear-shaped, but it's different. It is hm, okay, times a squared, and then divided by x squared divided by a squared plus y squared divided by a squared plus 1. A lot of people don't know the difference. They just put this way. It's normally what we use. Okay, in theoretical study, we put 3 halves here. Okay, instead of just this. Okay, and the reason we put 3 halves is because that will give us a very nice form of the Fourier transform. Okay, yeah. If you use this, you can use this. Okay, still looks like a pear-shaped, but when you do Fourier transform, it's not going to give you that nice form. Okay, so normally, okay, you have to pay attention to these 3 halves. Okay, and now once you know the h hat, the Fourier transform of the pear-shaped mountain, you can substitute into here. Okay, and then we get the solution in the Fourier space, but not in the real space. So we have ha squared divided by 2 times pi, and then e to the minus ak. This is capital K. Okay. Okay. This looks like simple, but it's difficult to solve analytically. Okay. So what you can do is you can, like Ron Smith, he did a couple of kind of asymptotic solutions at spatial, under spatial conditions, and then in general, if you wanted to have a general solution, okay, it's not easy. Even it's a linear, problem, it's not easy to transform back into the physical space. So what normally people do is you use the first Fourier transform. You do the kind of numerical simulation, calculation of this solution, and this solution involves the inverse Fourier transform. So that is called the Fourier transform, but they call fast Fourier transform because you usually apply the numerical method to do it. Okay, and there are some packages on online you can download and can try it. Okay, so for Ron Smith, he did an approximation, a form which is under the isostate approximation, which requires NA over U much greater than 1, and then he can solve the solution. Okay, so then he did some kind of non-dimensionalization. Okay, and that's normally what people do when you do a theoretical problem. You do some kind of non-dimensionalization, and in that way, you don't have to be kind of stick with specific kind of variables. you can have the nonlinear variable, which, okay, you can apply to different kind of situation. Okay. Okay, so then eventually he derived this eta theta. Okay, that's a non-dimensional. Okay, theta is a non-dimensional form of the eta, and eta is the vertical displacement. Okay, that's a displacement away, deflected from the undisturbed level, no matter which height you are talking about. And 1 over f is a flow number. Okay, as we defined before. So f is equals to u over n h. Okay, so that is flow number there. Okay, so this makes sense, right? Because if flow number is small, okay, that means what? U is small or h is large. Okay, that's higher mountain. And U small means slower flow, that you don't have enough kinetic energy to climb over mountain. Okay, so it's more nonlinear. Okay, and so when f is small, okay, and then eta will be larger. Okay, because you have nonlinearity. So larger. Okay, so then he applied the Fourier transform to do that, and also he has a linear theory too. Okay. And if you're interested, you can look at his 1980 paper published in Taylor's. Okay, if you cannot find it, I believe you should be able to find it from the online subscription by NCU. If not, let me know. I can send you a copy of his paper. It's a very well-known paper. Okay, 1980 Taylor's paper. Okay, so then. The key point here I want to go is we don't have time to go into very detail, but at least I have to show here is you have this. Okay, so here this is just imagine you are on an airplane on top of the mountain, and then the wave you see is this. Okay, is horizontal, and so at a nonlinear, a non-dimensional height of pi over 4, then you see this upward motion here. And that makes sense, right? Flow comes in. Okay, so you look at here. Okay, so say here is about, okay, n g over u. Okay, that's e g theta. That's a non-dimensional height. Okay, equals to pi over 4, and here, so you see upward motion here. Upward motion here, because face tilted. Okay, upstream, and here is the flow comes in. Okay, tilted like this. So the upward motion here, and followed by downward motion, and then on the side. Flow is easier to go over the mountain. So that's why, okay, if you chop it whole here, then you see just like two-dimensional wave, you have upward propagating wave. Okay, but on the side, the upward motion region is behave like U-shaped. Okay, like that. Okay, because flow here, because mountain is here, right? So highest peak is here. So flow will be forced to go up more, and on the side you don't. Why? Because you don't have much mountain height here, much disturbance here. So that's why it kind of big U-shaped, and then you go further up. Then this part become negative. Okay, and the positive part become like this. And the reason this is because just like 2D mountain wave. So then this part eventually, okay, is going to repeat. The mountain is going to repeat like this. At a certain height, we are going to have mountain like this. Certain height, we are going to have the disturbance like this, repeating the mountain, and this inverse. Okay, so here flow will be like this, and then flow will be like this. So then like this. Okay, sorry. Okay, so then over the mountain, you got downward motion, and then the upward motion. It's because you have the first tilt. You first tilt like this, you first tilt like this. Okay, and mountain, the disturbance is repeating itself with height. Okay. Okay, so and then Rossby, I think the main point I want to point out is here I let you read it. Okay, details. It's pretty easy to read because there are no equations. There are no equations. And the general upstream shift of the downward and upward displacement is caused by upstream first tilt, as I just mentioned. Because of this, so here upward motion is ahead of upstream of the mountain, but okay, higher up it could be down and then followed by upward motion. Okay, so it's going to repeating this kind of disturbance with height. Okay, so the U-shaped pattern of the vertical displacements are explained by a group velocity argument. Okay, so I don't think I have time to go over this, but I kind of at least go through the procedure. Okay, how do you get it? First, you base on 3.6.10. Okay, that then we can reduce. You can obtain this equation, and this equation is called dispersion duration. Dispersion duration. Okay. And dispersion duration is a general relationship, okay, which link the omega, the frequency, with wave numbers. Okay, so when you assume like when you assume a kind of like a normal mode approach, like eta or W equals to W head, okay, equals to eta head, okay, doesn't matter which variable, okay, and then you have e to the I of kx plus Ly, okay, e to the minus ikx plus Ly, this kind of normal mode approach, okay, or you do Fourier transform, okay, then you transform everything. Okay, you transfer everything. Here is not everything, of course. We only transfer like x, y to k and l, right? Because here we assume in x direction and y direction sinusoidal, okay, and we do that too for Fourier transform, okay, and then okay, you transform your variable into the side, become k and l, and then also you have t, that's the time, become what? Time becomes what? Time becomes what? In free space or wave number space. Okay, when we say this, okay, we transform, and then we transform equations into, we call the wave number space. Okay, wave number space, and if we do eta to eta head equals to 1 over 2 pi, or maybe square here, negative to infinity to plus infinity, eta, and then e to the I, negative I, kx plus Ly. Okay, and then dx and dy. Okay, so when you do this kind of normal mode approach, this we call wave number space. When we do Fourier transform, okay, Fourier transform, okay, and this is normal mode approach. It's similar. Okay, you do this. I think. We do this to negative, okay, so negative, we do this, and this is called Fourier space. This is called wave number space, this is called Fourier space. Okay, and once you got solution there, in a lot of problems, you can get solution here, analytical solution. But when you transform back, normally it will be difficult. Okay, so sometimes you have to apply kind of approximation, or asymptotic solutions, or apply the numerical method to do Fourier transform back. Okay, so once you got solution here, you have to transform back here. But it's easier for normal mode, but not easy because here you assume only one wave number, and here you have a spectrum of wave numbers. Okay, which is actually infinite number of wave numbers. Okay, waves. Okay, so this becomes omega. Okay, so now if you transform your equation, okay, into the equation in Fourier space, okay, or wave number space, then here you only left omega KL, and sometimes you even have the G. Okay, so sometimes you even have G here, and then that you have M here. Okay, like our current case, three-dimensional, T, X, Y, G, and in this case, of course, you do kind of normal mode in Kx plus Ly plus Mg. Then you are left equations with K omega, K, L, and M. So your wave frequency can be a function of K, L, and M wave numbers. So you are making the link relation between the wave frequency and wave numbers. And this equation is called dispersion relation. And that gives us omega equals to things like this. And for hydrostatic approximation, then what happens is these two horizontal wave numbers are much smaller than m squared. Okay, so then the downstairs, okay, the denominator become m. So we got m here, okay. And upstairs, we still positive, negative n times k. Okay, so then, as we discussed earlier, okay, then as long as we can get omega as function of K, L, and M, K, L, and M, then we can take partial omega, partial K to get the group velocity in X direction, and then in Y direction, in G direction, okay. And then if we are talking about the steady state flow, okay, we talk about steady state flow, then we have this capital omega equals to small omega plus what? Anybody remember that? Probably minus Ku. Okay, minus Ku. And then so say if this is equal to 0, then omega is equals to Ku. Okay, so then that means steady state, and then omega will be replaced by Ku. So then you can replace this omega by Ku. Okay, Ku, and then that's you can get the kind of steady state wave energy propagation in X, Y, and Z direction. Okay. And then now, that is along with a wave, but if you're fixed with a mountain, then you add another U to X direction. Okay, then you get this CGMX UL square over K square. Okay, like this. Okay, now since the group velocity is representing the propagation, okay, of the wave energy, so then X over G will be equals to CGM X in X direction, group velocity over CGG, okay, and then y over g equals to cgmy, cgg, like this, okay? And then you can manipulate, okay? You can manipulate, okay? Because you have cgmx, cgmg, you can this one, and so these two can be substituted. Okay, so what does this mean is, let me give a little bit more to explain that. So say you have mountain here. So say if your wave energy propagate to here, okay, your wave propagate here, then this wave energy propagation velocity will be composed by two parts. Right? It's good velocity. So this is Cg, like this, Cg m, and this is okay. Let me do this. Sometimes I write vectors in this way. Okay, that's same as the error there. Then this equals to what? You have Cg m. That means fixed with a mountain, that reference frame, and then g here. And what's this one? Cg m. That means good velocity. Okay, in the moving frame reference with the mountain. Okay, and then times x. Okay, so this is the x direction of the wave propagation, wave energy propagation. This g direction, the wave propagation, like this way, right? So this is cgmg divided by cgmx. Okay, because in that space you have this one go to here. So this is x, this is g. So equals to g over x. That's what we have there. Okay, that's what we have. Okay. Okay, so this one goes from this point to his point. So in space, this will be height. This will be horizontal distance. This is vertical distance. That's g over x. That will be parallel to this cgmx mg divided by cgmx. Okay. So this will be, this distance will be x, will be g. This will be g. This will be x. Okay, so g divided by x will be equals to cgmg divided by cgmx. Okay, and once you do that, you can plug all those into there, and then we get we get like this. Okay, this one, y squared equals to nax divided by g. So what does that mean? At a certain height g, okay, a certain height g, okay, so at certain height, okay, say g1, then according to 5.4.27, y squared will be equals to what? Will be equals to nax, and then divided by u, and times say g1, g1 particular height. Okay, so g1, and this will be equals to na g1 divided by u times x. So n, okay, assume it's constant. Okay, with height too constant. A is mountain head width, mountain scale also constant. And G1 now is certain height, that's constant. So this is constant. Okay, so y squared equals to, now y squared is equals to just simply alpha x. So what's this? That's a parabola, power sin. That's power sin, right? That's power sin, right? Because y squared equals to alpha x. Okay, so and that explains this power scene. That explains this U-shaped, this power scene. Okay, that's this power scene. This is certain height. At this certain height, okay, like g theta equals to pi over 4. That's power scene. Okay, the power scene like this. And here other height, then you have another power scene. Okay, and that it was explained by Rossby in his 1980 paper. Okay, for three-dimensional linear wave passing over mountain. Okay, so I let you read this. I think I already explained. Okay, and okay, so now the pear-shaped, the U-shaped disturbance over the mountain is certain height and certain height, all are like this. Okay, parabola, and this parabola, okay, when you plot it, it looks like the English U pattern. Okay, so then other phenomena I think we can talk about in next hour. Okay, I think it's time up. So we'll take about 10 minutes break. Okay, 10 minutes break. So we'll come here about 11:07. Okay, 11:07 we're okay for the next lecture. And I believe we can finish this part in next lecture. Okay, this chapter. Okay, because now we can focus on the concepts. Okay, and there will be some derivations of equations, but probably I'll just show you how to do it. Okay, and because some of them probably easy to do, but some of them probably not that straightforward to do. Okay, that need you to kind of download like lecture note and my book chapters, and then start it, and probably also need to go to the if necessary need to go to the original papers, okay, to read it, to try to derive it. Okay, but at least I kind of give you the concepts which you understand when you see some phenomena coming up, okay, or flow patterns from your observations or from the numerical simulations. Then you know how to interpret, and you know where to go to more the theories, to apply the theories to explain the phenomena. Okay. Okay, so we'll take 10-minute break. So come back here about the 11:07, 11:05. Okay, 11:05. Okay, thanks. Okay, so remember in two-dimensional linear theory, when we have so say we have constant U, okay, and then if say we have a N1 and N2, and N1 is much greater than N2, okay, and so there's a gap. Remember we have that. Then what happened when N1 is much greater than N2? There's a criteria. Then what happened is, so say you have mountain here, and it's going to have this kind of wave. Like this. So what is called? Lee waves. Okay. And so now, if we allow the N varies, okay, or N constant, U varies, okay, then we can, for three-dimensional flow, we also can get D waves too. Okay, we also can get D waves. So if we allow, in general, if we allow the scalar parameter varies at then that can lead to the formation of trapped D waves. Okay, remember we have two-dimensional like that, and now for three-dimensional flow, the trapped D waves will be similar to that of the Kelvin shift wave. Okay, like this. So if nobody tell you, or you show this to your friends, okay, they have no background in meteorology, okay, you show it to them, okay, they probably ask you back, oh, okay, where is this ocean? And okay, there are so many ships, okay, but they are not. They are, okay, mountainous islands with mountains, and when conditions are right, then you can see all those kind of waves, okay, like that. And so I probably need you to read the details, okay, but what happened here is, okay, this kind of wave, okay, is composed by two different types of waves, okay. One is you have this kind of repeating, okay, and perpendicular to the wind. We call it transverse wave because it's transverse to the basic wind. Basic wind go from left to right. Okay, and then here, in this wave, actually it is similar to two-dimensional, okay, D wave. Okay, so this part, transverse wave, okay, transverse wave is like this, repeating. Okay, and this part of the wave, okay, are just like the weight waves we discussed. Okay, and now you're fighting against the wind flow, so then kind of diverge out. It's called diverging wave. Okay, so we have diverging waves like this, and also D waves like this, composed. So then that gives us the wave pattern like this. Okay, so that's Kelvin wave, deep sea waves. Okay, so there's one paper have been kind of studied this very well, which is by Sherman and Utere in 1983. Okay, Sherman and Utere. Okay, and Sherman right now he is working at NCAR, studying the. He's quite well known in that area, studying the aviation turbulence and shifting problems. And Utere was his PhD advisor at UCLA. So this paper will be kind of provide a lot of guidance of, okay, details, dynamics of these two types of waves. Okay. Okay, so the transverse wave lie approximately perpendicular to the flow. Okay, that's transverse wave. That's those transverse waves perpendicular to the flow from left to right. Okay, so they are just like this type of waves. Okay, this type of waves. Okay, in the middle of the central line across the mountain. And so the formation mechanism of transverse waves is the same as that of two-dimensional chirp waves. Okay, unlike the transverse waves, the divergence wave, okay, attempts to propagate laterally away from the mountain, okay, and have been attracted to the D, okay. And remember, we have this when we have this kind of three-dimensional wave. Then we got upward motion like this, and then, okay, upward motion like this, and upward motion like this. Okay, those are upward motion, okay, upward motion. And then followed by downward motion, And then they kind of tilted upstream, and those waves are U-shaped, okay. But in that, so those waves are responsible for the divergent waves. Okay, but divergence waves are kind of more like ship waves instead of like U-shaped wave, and the reason is because here we have also have trapping. Okay, So that make it kind of diverging out and try to propagate upstream. No, try to propagate up, but then, okay, because of this cap, and then so it's going to try to diverge out horizontally because it have harder time to propagate up due to this cap. Okay, because here you don't have much wave disturbance because of this structure. So a lot of waves are here. So wave energy are kind of trapped. So it's not going to behave like this. Okay, instead it's kind of here. It can diverge out. Okay, so try to propagate. Okay, horizontally out instead of vertically. It tried, but it didn't. Okay, so a lot of them go like this. You know what I mean? Okay, so remember for the poetic waves, three-dimensional poetic waves, we have this. Remember this? We have U-shaped wave. We have like this. We have like this. See here? They are U-shaped. But the waves we look at diverging out is unlike this. It is go like this. Okay. It is because the adult wave energy are trapped here. Okay, trapped here. So the transverse wave will be repeating like the waves, but those kind of great waves, because it's trapped, wave energy trapped in the lower layer, so it's going to diverge out like that. Okay. Okay, now next topic is the generation of the vortices. Okay, and this is a very important topic because observations show we occasionally have a pair of vortices on this side of the mountain. Okay. So say here mountain, like mountain island, and then you can have goes out like streamline, kind of being spreading to the north, to the south, and then there's a pair of vortices like this. Okay, present at this side of the mountain. Okay, and sometimes this pair of vortices, okay, it's not, they are not symmetric. So then what happens is you have like this kind of positive vorticity, negative vorticity, positive vorticity, repeating, and then also propagating downstream. And this is called the von Karman vortex, okay, shading. Okay, so these phenomena are kind of going to be studied by this section 9.3, generation of the vortices. Okay. So this phenomena is not very new because in early time, 1960s, I don't know if you read that book, kind of fluid dynamics book by Becher. Okay, and okay, so here, okay, so say if when you're the high flow rumble flow, then wave behavior would be like what we just started in last lecture. Okay, then we got upward propagating wave, and then wave can pass over the mountain. But when the flow rumble is small, okay, so when flow number U over NH, okay, decreases, becomes smaller, U becomes small, or H become larger, okay, or M become larger, or a combination of those. U becomes smaller, H become larger, okay. And then this implies we have more nonlinear flow, more nonlinearity, okay. And then linear theory will not work. So a lot of times people are studying this kind of phenomena because it's so nonlinear. So they studied by numerical simulations, idealized, okay, or real case. And other way to do it is by tank experiment. Okay, you do tank experiment. So you have put a tank. You kind of put. Oh, you have to be careful now, right? I'm not okay. So you can build up a tank, water tank like this. Okay. And then you put a kind of artificial mountain. Okay. And then you make a flow going over mountain, and then suck the flow out, and then put the flow in. No, it's difficult. It's difficult. It's a tank. It's difficult to kind of force a flow passing over the mountain, and then you have the flow coming back, and then that's difficult. So what people do is you tow the mountain. So you are more or less you're kind of in the moving frame of the flow, and so you tow it. Okay, so flow kind of passing over you. Okay, so you tow it by a speed u, and that is mimic the real situation. You have u passing over the mountain. Okay, like that, and that's what people do in the tank experiment. Okay, and so people either do the laboratory experiment, the tank experiment, or they do numerical experiments to study the problem. Okay, so here, and you also can do it on the wind tunnel. You can also do it wind tunnel, but wind tunnel is more difficult to control for some parameters or some experiments. Sometimes they do that. Sometimes they, for air pollution problem. Okay, they do that. Okay. And so here, this is one example have been done before. So then you have different kind of flow phenomena. Like for example, when you have small flow number, okay. Small flow number, then you got higher linearity, and then that means the flow doesn't have enough energy to climbing over the mountain. Either mountain too high, or flow too slow, or then stratification is too strong. Okay, or a combination of all of them. Okay, U, N, and H. So you don't have enough energy climbing over. So then what is going to happen? You come to here at certain point, certain height. Okay, maybe higher part you can go over, but lower part you cannot. So you intercept into the mountain here, and then but flow cannot penetrate the mountain, so it's going to split. It's going to split. Okay, horizontally going to split. Vertically, it's going to be blocked and coming down and return flow. Okay, so then what happened here is upper part you can pass over. You can pass over, but at a certain point. Flow cannot go over. Okay, so then it's deep down, it's split. Okay, that part, and that part is called the attachment point. This attachment point. This is the plan view. Plan view. You go on top and look down at the mountain. Like that. So here, you have attachment point. Okay, because the flow come to here. Okay, cannot go anymore, and then you just have to split. Okay, and that you have the flow splitting. That phenomenon is called flow splitting. Okay, flow comes in, doesn't have enough energy to go up at this point. Upper part you can go over, but you cannot here. So it's going to go sideways. That's called splitting, flow splitting. And this point is called the attachment point. And then below that, flow will return, coming back. And when it comes back, will meet the basic flow coming in, incoming flow. And then at a certain point, you got to have a point which has no velocity at all, because the return flow is as strong as the basic flow. So at some point, okay, could it be close to the mountain, could be away from the mountain. Okay, if barking is very strong, could be further away from the mountain. Barking is less strong, could be close to the mountain. And then at that point, it becomes, okay, no velocity. Okay, so your U is equals to capital U plus U prime. Okay. Okay, so this is 0. At this point, it's kind of, we call it the saddle point. Okay, we call it saddle point. Okay, so we call it saddle because here, flow have to split. Okay, but here also flow coming back here. Flow coming back here, bump into it. Okay, so then flow coming back, bump into flow coming here, so they go out. Okay, and the shape is just like the shadow. When when you are writing a horse, okay, that shape. Okay, it's called shadow point. And then on this side, okay, on this side, then you have, because you have flow splitting, and to this side, you cannot point mouse. Okay, here, split. And split, and then there's a return flow here. There's a return flow here. Okay, so so here, flow split, and here you have return flow. And at a certain point, inside this circulation, there's no motion. And those motions, these are called knot, N-O-T-E, knot. Okay. Okay, so I have some explanation here. Okay, so the formation of this pair or D vortices. Okay, this is a pair or D vortices now formed because of flow splitting. Okay, low flow, rumble flow, and come here, and then recirculate. Okay, and then a pair of D vortices formed. Okay, and one has positive vorticity here to the south, and to the north we have n-type vorticity here, negative vorticity here. Okay. So you have this pair of vortices, and they are called D vortices. Okay, and this pair of D vortices has been attributed to the boundary layer separation. This is called boundary layer separation. Okay, boundary layer separation. Okay, and so this is split. Okay, it's called boundary layer separation, and then flow goes around the mountain, and then return back on this side and form two D vortices. So this phenomenon has been known for a long time and has been explained okay, by like Becher's a book, 1967 book, and by Hunt and Snyder. They are at the US EPA. They did okay, tank experiment, okay, and studied the problem. Okay, so then I have explanation here. Okay, so when the Reynolds number, okay, remember here, there's difference from what we studied earlier. Okay, we studied earlier, we assume there's no friction. Here, there's friction. So that's why we have Reynolds number. Haha, question for you. How many people know the Reynolds number? What's a Reynolds number? Think. What's a Reynolds number?
The ratio of inertial force and
viscosity. And the ratio of viscosity and U error, right? Yeah, okay. Okay, and what's U error? U is basic wind speed, of course. Error is horizontal. Okay. The obstacle scale, the mountain scale. Okay. U error over mu. So how do you get that U L over nu? How do you get that? Okay. You go to equations. Okay, yeah. You go to equations. So say, for example, you look at the U dt minus Fv equals to negative 1 over rho naught partial P partial X. Okay. So if with the U dt divided by Fv, what's that? That's Rossby number. Okay, because this U divided by T, okay, and F, and then this will be U, right? So this will be equals to U over, but T is time. Okay, it's time. So say you have the scale of the mountain L or some phenomena L divided by U. Okay, so then this will be L divided by U, and then Fu. Okay, so U over T Fu, U. Yeah, right, that's correct. Okay, so then this becomes U over Fl. That's Rossby number. Okay, now if you have the friction, mu del square U. A simple one, okay. This is, we call molecular viscosity, okay. Of course, a lot of things are not explained by molecular viscosity, but a simple form like that, okay. And so we have this. Now, if we do du dt scale analysis by nu del square U equals to U divided by T divided by nu. Okay, and assuming this one is approximated by T square U dx square. Not necessarily true, okay. Yeah, not necessarily true, okay. But okay, hey, people do that. Okay, so then you have this U divided by what? L square. Okay, so this is equals to U divided by same thing. L divided by U, and then you have nu U, okay, and then you have L square. So that gives us L cancel out, okay, and then one U cancel, this U cancel out, okay, this U cancel out, right, okay, and this L cancel one out. So then we have U times L divided by mu, and this is called Reynolds number. Okay. Yeah. So that's okay. So when Reynolds number is large, when Reynolds number is large, that means either U, L are large or nu is small. Okay, so that's what we did earlier. We assume it's implicit, no friction, or friction effect is kind of negligible, very small. Okay, and if nu is appreciable, large, then Reynolds number will be small. Then you have to take care of viscosity. Okay, you have to include the viscous effect, friction effect. Okay, so then when the Reynolds number is sufficiently high, okay, then the boundary layer will develop a region of, let me see, number is sufficiently high. The boundary layer will develop a region of rho reversal near the surface due to approaching pressure gradient in the direction of rho. And let's see, U over mu, I guess probably is low, not high. Okay. Let me double check. Okay. And the reversal flow means the incoming flow, and you form a stagnation point. Okay. So here, when you have, okay, flow comes in and come in, and then you have U. Okay. So here you've got attachment point here. Attachment point. Okay, coming in, and here then you've got that stagnation point. Stagnation point. Okay. Okay. So mathematically, the streamline or boundary layer separation is a line where points are singular point. Okay. Flow comes in, split, and then so you have an air parcel or fluid particle. You can go this way or go this way, and that's called the singularity. Okay. Okay. Or other way to say it, you have bifurcation. In mathematical term, it's bifurcation because, okay, it's a point. You can go this way or go this way. For 3D nonlinear stratified viscous flow, that means with friction, past a symmetric mountain, boundary layer separation first occurs on the center vertical plane. On the center vertical plane, okay, center vertical plane. That's like this. Okay, this mountain, the center vertical plane, you occur that. And before the mountain peak is reached. During the process, there are several single points. I did illustrate it, okay, because they are kind of very detailed. And I explained already. Attachment point, that's mode of attachment. That's NA, this attachment point. Your stagnation point. Your settle point or separation. This is settle point or separation too. Okay, that is. Okay, settle point of separation. Okay. And you have the flow splitting. This phenomena is called flow splitting because low flow number flow comes in and then split, flow split to go around the mountain. Okay. The flow number is decreased further. The flow pattern persists, but NA moves closer to the mountain peak, and then the vortices expand further downstream. Okay, now this has been known for some time. Okay, now in 1989, Smarkiewicz and Rotuno. They draw a numerical model, and then they turn off the friction. Okay, and they found they have no friction, so they still have the vortices generated. So then that kind of get them excited, and they try to explain what happened there, because no friction. Okay, they turned all the friction terms off. Okay, so that's what I tried, and then okay, so in their study, okay, so when flow number is large, okay, then okay, you still have the flow splitting, but you don't have the vortices formed. When it's small, then you have pair of vortices. Okay, positive vorticity here, negative vorticity here. Okay, kind of intercyclic flow. Intercyclic vorticity, and here is cyclic vorticity form. Okay, and these two regimes, they call this is flow over regime, or three-dimensional flow over regime, and this called flow R1. Okay, flow R1 in the mountain. Okay, they have two regimes here. Okay, one is flow over. Okay, regime. Okay, that's high flow number. And second one is flow R1 regime. Okay, that's low flow number. Okay, so what they try to explain is, okay, so here you can see very beautifully, you can see, okay, flow try to go over, and then you got, okay, kind of jumping up, okay, and then you got wave generated. So you can see the upstream propagating wave, you can see upstream propagating wave. This is, okay, mountain waves. Okay, those are upward propagating waves. And then, but for this one, you see here, you don't have much disturbance above the mountain because the flow, incoming flow just doesn't have enough energy to climb it over. So you have to go around, and go around we form the vortices. And not only that, here, you also, what happened here is you have the upward motion here. Okay, what happened? Okay, is because, okay, so say this is a mountain, and with low flow number flow comes in, they don't have much energy to convert, okay, to potential energy to climb over. So then go around, and then, okay, you have the vortices formed coming here. But the vortices come here, they have flow convergence here, and that generates vertical motion. That's this part, vertical motion, this part. Okay, this part is you have two the vortices, and the flow come here, they have convergence, and they generate upward motion. That's this part. Okay, and here you have flow going over, and then return back, coming here. Okay, and so this is attachment point here. Attachment point here. Okay, this is due to the vortices. Okay, and flow converge, and then nowhere to go, just go up. Okay, so the similar results agree very well with the laboratory tank experiment. Okay, like Snyder, okay, the previous figure as shown in 520. Okay, now the problem is they apply free slip low bound conditions, and there's no explicit surface friction. So where does the vorticity coming from? Okay, so they try to explain that. Okay, and so when the flow number is reduced to below 0.5, and in this case, flow number is 0.22. That's in 5.21b, the one on the right hand side. Okay, and so these are phenomena I just explained. Okay, so a pair of counter-rotating vortices. One is cyclonic, one is anti-cyclonic, form on the this side. Okay, and similar to observed in the tank experiment. And the region of downward disturbance is enlarged. The great wave response is dramatically reduced. Okay, so then you don't have much flow disturbance above the mountain. Okay, and go around. So you have two regimes. Okay, this is flow around regime. The second regime, low flow number. Okay, this is high flow number. Okay, based on the long-dimensional mountain height, NH over U, also is called inverse Fourier Transform flow number, and horizontal mountain aspect ratio. Okay, B over A. Your parameters, like sometimes your mountain is not necessary to be rounded. It could be kind of more wider. Okay, kind of perpendicular to the floor, or could be slender, okay, in flow direction. And so based on these two parameters, non-dimensional parameters, then you can have different kind of flow, okay, weather phenomena observed. You can have the linear mountain waves, you can have the wave breaking, you can have the flow splitting, the vortices. Okay, so this is This one was based on Smith 1989 paper and Epifanio 2003. Okay, and I sketched it all their result together. Okay, so I kind of sketched it this based on their results. Okay, kind of conceptual model. Okay, so you have NH over U, that's inverse Fourier transform. So inverse four number, and P over A. What's A? A is the have width in X direction. P is in Y direction, perpendicular to the floor. X is following the floor direction. Okay, so this one is P over A greater than 1 or less than 1. This is P, this is A. So this is P over A less than 1. Okay, so 0.5. And here is, so here we have no more bracket here, right? Here will be this bracket here. So then you have different kind of phenomena here. Okay, we're breaking. Okay, so when you have NH over U is small, like lower mountain, okay, stronger wind, then you got linear mountain wave. Okay, you got P over A, large. Then you, okay, small large is kind of you got okay, kind of mountain waves. Okay, and then here you got D vortices occur. Okay, floor splitting. Okay, D vortices. Okay, wave breaking here. Okay, now key question is why we have this D vortices form without the vorticity. Okay, what's the source of vorticity? Okay, so, and there are two theories. Okay, here is other problem come into argument. Okay, so they argued. Okay, and different group. Okay, and so the first group is they call the tilting of volcanically generated vorticity. Okay, and kind of proposed by Smarty and Dotuna in 1989, and other group is led by Smith, and then Sheehan and Smith. Okay, they say generation of internal potential vorticity by turbulence dissipation in numerical simulations. Okay, so apparently we cannot get down this. Okay, so we try to get down in this afternoon. Okay, so. Okay, we'll talk about this. Okay, the equations, and as you know, this term is called what term? What term is this? This is advection, right? Advection of the vorticity. This is three-dimensional vorticity, by the way, and this term is stretching term. Okay, and what's this term? Solenoidal term. Solenoid term. Okay, yeah. So we have this. I explained this in this afternoon. Okay, in this afternoon. Okay, we're fast. So enjoy your lunch. Okay. Yeah. Okay, so 5.4.28 is the three-dimensional vorticity equation. Yeah, and this is inviscid. There's no friction. So this one, because this is what Smarty and Dotuna wants, because they try to find the source of vorticity in an inviscid flow. Okay, no friction, frictionless flow. So here, no friction. So they try to find it. And as you know, the omega is a three-dimensional, okay, vorticity. Okay, so omega has three components. The x component vorticity is xi, and then y direction is eta, and then zeta. Okay, zeta is normally what we are looking at. Okay, we are interested. Vertical vorticity. Okay, vertical vorticity. That's eta, zeta. Okay. So the first term okay, equals to negative, sorry. Okay, so partial omega partial t equals to negative v. Okay, this is okay vector. So dot there, and omega plus omega dot there, and times v. Okay, this means vector. Okay, and plus delta p plus delta rho divided by rho square. Okay, like that. And as you know, this is local rate of change of the vertical, the vorticity vector. Okay, and this one is advection term, advection or vorticity advection, vorticity advection. And this term is the stretching term. Okay, stretching term. Okay, or convergence term. Okay, because if we look at this one, if we look at just vertical component, then what we have is the vertical component. Okay, what we have is we have this. Okay, this one will give us omega dot there. That will give us the following. Okay, we have the omega. We have three components. That's xi. Okay, partial x. Okay, and plus eta partial y. Okay, plus zeta partial g. Okay, so component. Okay, and then this is the component, and this one has three components, u, v, w. So the vertical component will give us the zeta partial w partial g. So this is stretching term. Okay, and this is called solenoid term. Okay, solenoid term. And solenoid term can be understood if you look at like, so say we have pressure like this. Okay, so say we have low pressure here, we have high pressure here. Okay, and then we have pressure here, so then we have say P1, P2, P3, P4, like that. Okay, and then if we have so if say we have the core air here. If core air is here, then there's no solenoid term. If core air there, like that, so then we have rho 1, rho 2, rho 3, rho 4. Okay, core air, so it's, I probably should say 4, 3, 2, and 1 here. Okay, 1 here. So rho 4 greater than rho 3. Okay, like that. Okay, so then if you say at this point, these 2 points, like that, then what's the pressure gradient force? In this direction, right? Okay, in this direction. So we have pressure gradient force in this direction, in this direction. Which one is larger? Okay, this is PGF, right? This is PGF. So PGF is equals to negative 1 over rho. Okay, partial P, partial Y, right? Partial Y, right? Because see, okay, because the pressure is in east-west direction. So like this. So don't look at okay. We just look at the absolute value. Okay, that is equals to 1 dp dy. Okay, dp dy is the same. dp dy is the same. Okay, right. So rho here is rho 2. So here is rho 2. Here is rho 3. But rho 3 is larger than rho 2. So that means low 2. Okay, larger low 2. That means the pressure gradient force is larger here. It's smaller here. So then we are going to have rotation, vorticity generated by, and that is called the solenoidal term. Okay. Okay, and also you can look at a special case like if the aspect ratio of the obstacle height h, okay, over h over a, okay, is small, then this solenoidal term can be reduced to this, and then that becomes simpler. Okay, so then you have the buoyancy kind of gradient, and then times cross k, and then take a negative, then that gives solenoid term. Okay. So here we can also look at here too. Okay, so here, so at this point, what's there B? What's there B? The buoyancy. Okay, so buoyancy is related to density. Okay, so the density gradient is which direction is, okay, it's this direction, okay, this direction. So buoyancy force will be opposite to that, okay, to this, so it will be this direction, okay, this is called this wall here, okay, so it will be this direction, and then K, okay, K is out, and then so K cross that, and then negative. Okay, so that will give us circulation. Okay, so that you figure it out. Okay, so anyway, so if we look at this, then I think the easy way for you to understand is, okay, this sketch is done by me. Okay, done by me. I try to kind of using this to visualize the argument by smart keywords and nocturnal. Okay, so this is easier to understand. So say here. Okay, so say this is U is into the ball. So say your wind is blowing into the ball like that. Okay, and then what's going to happen? We're blowing into the board. It's going to go up. Right. Right. Agree? Okay, air coming in, bump into the mountain, it's going to go up. Okay, go up. Okay, so what happens when air goes up? Become colder, right? Because it's been squeezed, been expanding. So air parcel coming to here, go up, expand, become colder. Okay, so colder will sink down. Okay, compared to here. Okay, because here mountain is lower, right? So your go down will be less. So then eventually on the right hand side you have this kind of vorticity. And what kind of vorticity is that? That is go this way. Because go down, okay, so go like this, go like this. So that vorticity is in x direction, horizontal vorticity. That is in opposite x direction, go this way. Here, you go down, okay, you turn this way, that will be into the board, that's positive vorticity. Okay, xi greater than 0, xi less than 0. Okay, so now when you have this, okay, so you have this kind of vorticity, horizontal, and then you try to go over the mountain. So on the right hand side, so air coming in will go up, will become colder by adiabatic cooling. And then so this part is colder, so it's going to sink down more compared to this part. So then you have vorticity go like this, and that will go to here. become vertical vorticity. Okay, horizontal vorticity. Okay, go around the mountain, three-dimensional, and then it will become vertical. And here will be just object. So here you have a positive vorticity here, here a negative vorticity here. So you have pair of vorticity under this side. And that explains their theory without friction. With the friction, you can have the separation or boundary layer separation to generate a pair of deep vortices. Without, that's their explanation. Okay, so that's their theory. Okay. Okay, you can also apply this equation, kind of simplified equation, okay, for lower mountain case to explain this, okay, vorticity, okay. This B is negative, that buoyancy is negative, okay. So that gives you this horizontal vorticity and that swipe, okay, that this vorticity swipe will become vertical vorticity, okay. Okay, so that's their theory. That and then the Rossby doesn't agree to their theory. So then he proposed the generation of potential vorticity by turbulent dissipation. Okay. He said at a later stage, the associated thermal anomaly generated by volcanicity are eroded by dissipative diffusion process. And during the stage, the flow is controlled by dissipation and is accompanied by PV generation over a long-dimensional time of order of 10 to order of 100. This is proposed by Scheer and Duran. In other words, Scheer and Duran doesn't really disagree with smart cubics and autonomous volcanic generated vorticity, but they say that occurred in the early stage when the time period is in order of 1. And then at the later time, from order of 10, non-dimensional time, to order of 100, okay, then dominated by Rossby theory, okay. That's the potential vorticity, okay, generation. And as you know, potential vorticity is conserved in a adiabatic and inviscid fluid. But when you have friction, you can generate vorticity. Okay, you can have dissipation of vorticity. When you have diabatic heating or cooling, you can also have generation and dissipation of potential vorticity. So he has argument. His argument is this. Okay, maybe easier to look at the upper one. That's Rossby's argument. So here, his argument is when your flow comes in, and this flow is low flow number coming in, and then blocked by the mountain, then you have overturning, and then here you got turbulence generated, and turbulence is generated, and that turbulence will kind of go around here, the turbulence flow go around here and generate positive vorticity. And then left-hand side will generate negative vorticity. So then this potential vorticity generated will spin up, okay, induce the vertical vorticity, okay, positive. And the one is induce negative vorticity here, okay. So his argument is because your potential vorticity is not conserved, and they are not conserved is they can be generated, okay, can be positive, negative, generated at the turbulence region, okay. And turbulence region is this blocking, and also you have the wave overturning here. When you have wave overturning here, then you can generate turbulence, and then you generate positive and negative vorticity here. Okay, so that's his argument. Okay, and there are some more dynamics for this kind of dissipative generation of potential vorticity. So I kind of highlighted in a way. Okay, so I let you read it. Okay, we did it, and this part will not be part of the final. Okay, just for your reference. Okay, in case you are interested in the argument and you wanted to know more about the dynamics. Okay, those are more in-depth argument. Okay, so I let you to read it. Those parts will not be included in the final. Okay, you are encouraged to read, but not required. Yes.
What time is the final exam? What time we will check final exam on the next Tuesday?
Next Tuesday, yeah, it's
morning
in the morning. Yeah.
morning.
It's okay? No? Morning is okay, right? Or you want the afternoon? Morning is okay, huh? Yeah. And probably will take 2 hours, okay? So, what I can help you is, okay, the final will be, I may have some kind of problems, but they probably will not the majority of the problem. Majority of the final will be kind of short questions, concepts, short questions. If there's some calculation, it will be short, okay? So, and also to help you, I try, not promise, I try to come up a guide, okay, of the final, a guide, okay? So I'm kind of condense some of the lectures, okay, and then so that's the part I require you to understand, okay, and you read that part.
So
and
you
then
are going to give us some briefing?
Yeah, some kind like before, okay, I come up a kind of a guide. Yeah, okay, so you can focus on those, and then you don't understand, you go back to the lecture note. If lecture note you can understand, you go back to the book chapters, okay, which you can download. Okay, yeah. I always worry about the students. Everybody is going to get 100. I always worry about that. Yeah. Right. Okay, so this part will be kind of further reading. Okay, you encourage you to read, but if you are busy, you can focus on those in kind of black and white, not in this kind of color. Okay, like this will be part of the final. Okay, so when the wake flow in which the D vortices are embedded becomes unstable, okay, the vortices tend to shed downstream. Okay, so in other words, when we have the mountain like this, we're blocking, we got flow spreading, we got vorticity generated. Pair of vortices generated. If those vortices are not stable, then what happened? And also not symmetric. Okay, then we have the vortex will become unstable, and then will be shaded downstream one by one. That's called vortex shading. Okay. So we have mountain here. Okay, we have like this. Okay, this. If those are not stable and not symmetric, so those will become like. So then we have split, and then we have one by one, like this. Okay, we have. This is okay, and then we have. Kind of one by one. Okay, so here like this. So it's positive vorticity, negative vorticity here, negative vorticity here, positive vorticity here, and this is called vortex setting. Okay, vortex setting. And so that's found by Theodor von Karman, a German, von Karman. Von Karman is a very famous fluid dynamicist. So that's also called the von Karman vortex sheet or von Karman vortex setting. Like this. The got vorticity setting. So here, what comes in, we generate the vorticity, pair of vorticity, but then one of them dominates and then set it, and then another negative one comes generated. So one by one, we have the vortex setting here. Okay, so that's chapter 9. Okay. Okay, so next topic is, so just a quick recap. We go from shallow water, flow, and we add stratification, and two-dimensional inviscid, and then, and then two-dimensional flow, mountain waves, and then we add nonlinearity. We talk about nonlinearity. So, and then later we talk about and then we add D waves, and then we talk about three-dimensional flow. And then we add the low flow number to it, nonlinearity to it. So then we have D vortices. And one thing is mentioned because we still assume the flow is non-rotating. So now we add rotation into it because now we are talking about the larger mesoscale mountains. Larger mesoscale mountains. And then in this case, we cannot ignore the rotational effect. So here we have three parts. One is rotational effects, and the second part is the cyclogenesis, and then orograph influence on cyclone tracks. The rotational effects. In the previous sections, effects of Earth rotation are ignored. And this is approximate value for flow with Rossby number, as you guys know, which is defined as U over FL. And L is the horizontal scale of the mountain. When this Rossby number is larger than 1, much larger than 1. Then we can ignore it. It's much larger than 1. But when it's about 1 or less than 1, we cannot ignore it. So when Rossby number equals to order of 1, or smaller, then we have to take into account, we have to consider the effect of the rotation. So in this case, the elevation time, L over U, is for the air parcel to pass over the mountain is too large to be ignored. Compared to the period of the oscillation, so we have to include rotational effect. That's the F. The chorus parameter F. So we have Rossby number equals to U over FL. So when this is equals to equals 1 over F divided by L divided by U. Okay. So this is inertial oscillation, okay, due to Earth rotation. And this is L divided by U. That's the time air parcel passed over mountain. L is the mountain width or scale. Okay. So this is oscillation. So when Rossby number is about 1, you cannot ignore this. Even only when Rossby number is very large than 1, then this is small. Okay, if this is much greater than 1, okay, that means this term is dominates compared to this term, the oscillation. Okay, so if it's about 1 or smaller, then you cannot ignore the rotation. Okay, so for flow past many mesoscale mountain ranges, such as European Alps, US Rockies, Canadian Rockies, Andes, and Scandinavian mountain range, the New Zealand Alps, and the Central Mountain Range of Taiwan, okay, they all belong to this category. And of course, if the Rossby number is very small, like Rossby number is equal or less than 0.2, then the flow can be approximated by quasi-geostrophic theory. Okay, and when the Rossby number is large, then we can ignore the rotation. Okay, that's what we have been doing so far. Okay, so in general, for flow over mesoscale mountains, okay, those numbers are on the order of 1. So in this case, the influence of the corresponding force is too large to be ignored. You cannot ignore it. It's there, okay, but too small to be approximated by the quasi-geostrophic theory. So it becomes kind of difficult to deal with, because you have to deal with that, but you cannot do like quasi-geostrophic theory. Okay. Okay. So if we consider the small amplitude, two-dimensional, partial y equals 0, steady state, inviscid, rotating, uniform. Okay, this is the important part. We add into it the new factor, and uniformly stratified Boudiensk flow over an infinitely long mountain ridge on an airplane. Okay, we just assume airplane. Okay, normally we don't consider, in mesoscale we don't consider F variant. Okay, in the model of course it's always there. Okay, because some model just they built up in that way. Okay, but for theory it's kind of rather difficult. If you want to include in beta effect, you can, but that time probably you have to apply the quasi-geostrophic theory. Okay, and then that has some simplification of the equations. Okay, to help you to do the problem. But for mesoscale normally we don't consider beta effect. So the governing equations can be derived from 3.6.1 to 3.6.5. So eventually we have this. So remember this, if we ignore this, okay. Probably let me write down here. So 5.5.1, then we have U square, partial square, partial x square. Okay. And then we have partial square w prime, partial x square, plus partial square w prime, partial g square, and then plus f square, partial square w prime, partial g square. Okay, plus a square, partial square w prime, partial g square. Okay, 0. Okay. So if we compare, say, this term, and compare to this term. Okay, and then that will be u square, d square, dx square, d square, w dg square, divided by f square, partial w partial f g square. Okay, will be like that. So this will be based on scale analysis you learned from atmospheric dynamics or dynamical meteorology. And then this will be roughly equals to u square, and then this will be L square, right? And this will be what? W. Okay, and then divided by G, that's LG square. Okay, this is vertical scale of the system. And then here will be F square, and then we have W. And then divided by LG square. Okay. So then, in this case, LG square cancel out, W cancel out. This will equals to U over FL square. That's Rossby number square. Okay. So if Rossby number is very large, okay, so if this is much greater than 1, okay, then that means this term is dominated of this term. Okay, so then this can be ignored. Okay, then the equations become, okay, u square partial x square, and then w prime dx square plus the square w prime dg square, and then plus n square. I think this is probably x square. Yeah, that's all. Okay. So this is x square. So x square here. So this is d square, w prime, dx square. Now, if we take differentiation from negative infinity to x, okay, on this twice. So we take twice, okay, and then x equals to negative infinity to x, okay, and then you do it twice. Okay, and equals to 0. Then this will reduce to, okay, then this okay will reduce to d square w prime dx square plus d square w prime dg square, and then plus n square over u square. That is core parameter for constant n and u, and then w prime equals 0. And that is what we have been studying before. Okay, so now it's correct. Okay, now no trick. We just play same trick before. Okay, so we just take integration. We just take the Fourier transform into the free space of this equation, okay, and then we can get the following. Okay, so everybody got this done. So okay, we have to keep it now. We have to keep it. Okay, so if we take the Fourier transform, okay, with respect to x. So that means our w hat will be equals to 1 over 2 pi. Okay, and then we have negative infinity to positive infinity. And then we have w prime. And then e to the negative I kx and then dx. Okay, then this will become what? This will become negative k square u square, negative k square w hat plus d square w hat dg square. Okay, and here it becomes f square d square w hat dg square. Here become negative k square n square and then w hat equals 0. Like that. Okay, so now it divided by k square u square. Then we're going to have negative k square w hat plus d square w hat dg square. Okay, and then minus f square divided by k square u square d square w hat dg square. Okay, and here become plus n square over u square and then w hat equals 0. Okay, so this is dtg square. So then, okay, we have 1 minus f square divided by k square times u square, d square w hat dg square. Okay, and then plus a square over u square minus k square w hat equals 0. Okay, so this will give us d square w hat dg square plus a square over u square minus k square 1 minus f square over k square times u square and w hat equals to 0. Okay, so this coefficient can be simplified because the coefficient okay will become the following. Okay, once you are done, we can take a break and then then come back in the next lecture. So this will give us what n square minus k square u square divided by u square. Okay, and then divided by k square u square minus f square divided by k square u square. Okay, so this will give us n square minus k square over u square divided by k square u square minus f square. Okay, and then u square cancel out. This will jump to upstairs. So yeah, so we are going to have k square here. Okay. And okay, so that's a coefficient. This coefficient, this, okay, we'll come back here. Okay, and then we have d square w hat dg square. Okay, and then plus k square times a square. Sorry, writing. So this is k square, a square minus k square times u square divided by k square u square minus f direct head equals 0. Okay. So if this is m, defined as m squared, you can solve it like before. Okay. It's just a more complicated situation because we have one parameter, 2, 3. Okay. Okay. So we n, k, u, and f. Okay. This is square here. And we have to determine, we have just more, little bit more complicated situation. Okay. Because instead of 2 variables, okay, we have 3. Okay, we have k, u, we have f, okay, and we have n. Okay, so we have to compare these 3, and just like we learned in the beginning, when we are dealing with the inertial gravity waves. Remember that? Okay, we also have similar situation. Okay, so now we have the background to do that problem. Okay, great. So let's take about 10 minutes break. Thanks. Okay, so m is equal to this, right? Yeah, that's identical. Okay, n squared over k squared over u squared. So m here is equals to, okay, like that. Okay, so we have, k squared times n squared minus k squared u squared divided by k squared u squared minus f squared. So it's determined by n squared, k u squared, and f squared. Okay, so this I just quoted from table 3.2. That is, we talk about in chapter 4 in the lecture notes. And so here you have different, see here, you have kappa squared. Kappa is k, that is 3-dimensional. Okay, so this is give us k squared plus l squared. Okay, and then otherwise it's the same. Okay, so we can have different kind of flow regimes. Okay, high frequency evanescent flow regime. We have extreme case, okay, potential flow, and non-rotating evanescent flow. Okay, so we have different kind of flow regimes. I'm not going to repeat. Okay, I think they are pretty easy to follow because because you have 3 variables to compare. You have n squared, you have ku squared, you have f squared. Okay, so you can compare these 3. Okay, and each one will give us different governing equations. Okay, when we ignore some terms, will give us ignore certain terms. And remember here, we are talking about kind of steady state flow. Okay, so there's no partial t or omega. There's no omega here. Okay, it's like omega is equals to ku for steady state. Okay, so here we have different regimes. Okay, so we already discussed 2 flow regimes in earlier sections. That is this one, and then this is that one. And then in the chapter 4, we talk about the non-rotating evanescent flow regime of k squared u squared greater than n squared, much greater than f squared, and n squared greater than k squared u squared, much greater than f squared. Okay, because that is, when it's much greater, that means it is not important. When these 2 terms, no matter they're greater or smaller, when both are them much greater than f squared, so not important. So that's what we did before, non-rotating. Okay, evanescent flow and non-rotating vertical propagating wave regimes. Okay. So to to demonstrate the rotational effects, we consider an extreme case of a flow past a very broad mountain ridge. Okay, so this is the case, just kind of demonstrated. Okay, to do this kind of problem. Okay. So assume a base-shaped mountain range like 5.2.5, its Fourier transform can be formed like this. Okay. So here is two-dimensional. So we assume, again, h of x is equals to hm and then a squared divided by x squared plus a squared. Okay, so then we can make Fourier transform. Okay, this will become h hat of k equals to hm divided by 2, and then a, and then e to the minus ka. Okay, and this is to assume k greater than 0. So we are doing the one-sided Fourier transform. We are. So when I do this, okay, I can hear clearly. That's better, right? Yeah. So, okay. So probably every time I talk, I do this. Okay, the above solution can be extended to. Probably I put it. Maybe I put it here. I put it here. Okay, so can I hear it? Okay, to quadrature flow over a three-dimensional isolated mountain. Okay, so let me see. So in this situation, we have n squared greater than f squared, much greater than k squared over u squared. And the vertical wave number reduces to m equals to I, k, n, f. Okay. So if we assume, sometimes I can feel I can hear better. I don't know, maybe I put it here so people watch us can hear it. Oh, this is better. Okay. I hope I don't eat it. Okay. So in this case, we have let me see, we have n squared greater than f squared, much greater than k squared and u squared. Okay, like this. So that means when f compared to k squared, u squared, then this is almost 0. Okay, and n squared also much greater than k squared, u squared. So this is almost 0. So the advection effect is small. So then m becomes square root of k squared, n squared over k squared, f squared over f squared. Okay. So then that equals to. So then we have this equals to positive negative k n over f, like that. Okay. So then m becomes. Oh, we have to be careful. We have a negative here, right? A negative here. So that gives us I. Okay. So that gives us, let's ignore positive, negative. So that gives I here. So then we have I, k, n divided by f. Okay, as discussed in chapter 4, the inertial gradient waves, this is the equivalent to make the quadrature approximation. Okay, so say if we have this case, then we can substitute h hat also, the h hat here. into 5.5.2. So what's 5.52? 5.5.2. That's this one. Okay, this is a solution. Here we already kind of put H hat K over there as the low bound condition already. Okay, and then here, because K for this is unlike the normal mode approach because we are using the Fourier transform. So that means K will be varying. Okay, it's kind of covered out of wave numbers. Okay, infinite number of waves. So then we have this. Okay, kind of K when less than L, and this is K greater than L. Okay, and so eta can be obtained by this one. Okay, this is similar to what we did before. Okay. Okay, so then you substitute that into it, and then you can get the solution which is like what you learned from atmospheric dynamics, okay, or dynamical meteorology. Then that's quasi-geostrophic approximation, and then you can actually solve it, okay, and get eta equals to this, okay, and assuming the k square u square, the elevation effect is small compared to F and N. Okay, then we got this solution. And then the above solution can be extended to quasi-geostrophic flow over a three-dimensional. You can even extend this to be three-dimensional. Okay, it shouldn't be that difficult. The difficult part is not solving the problem analytically on the Fourier space. The problem is to bring them back, those solutions back to the physical space. That's the most challenging one. Okay, but these days it's easier because okay, we have pretty good numerical software like the fast Fourier transform. You can, you guys are very lucky. You can just download and then you can apply to it. Okay. So this solution can be extended to three-dimensional, okay, and then that like shown in 5.26a, okay, like this one, okay. This one is with rotation, okay. So this was done by Smith, 1979, review paper, okay. It's a very good review paper, okay. The Smith 1979. And you should be able to find the reference from the book chapters I provided in the website. Okay. Also by Bucci and Tibati, okay, in 1977. Okay, these two are Italian scientists. So what happened here is, okay, you have flow coming from west, and then you have a slight increase of the air column. Okay. Sometimes some students they ask questions: is that true? Okay, because over the mountain you got column shrinking, no problem. Everybody knows that. Okay, everybody agrees to it, and you have air current comes in. How come you have a slight increase of the air column? Okay, you don't believe it. Okay, you go home, and then what you can do is, okay, what you can do is like this. So say you just idealize your mountain like this. Okay, like this, and then here, say tropopause. It's not, okay, I don't know if you have read, probably not at your age, because I have collected Horton's, okay, edition 1, edition 2, edition 3, 4, 5. Okay, in earlier version of Horton's, he is kind of rigid it. When you're rigid it, okay, you have air current like this, we're always shrinking to here, okay? But you go home, you do this. So say you have some disturbance, but not as large as on the ground, but okay, like this. And then you do this, and you do that, like just idealize it. A disturbance like this. Okay, and then you measure it, you'll find this part actually is slightly stretched. The air current stretched, okay, near the mountain here. Okay, that's why here it's sketched like this. And then once you're stretching, what happened? Okay, you probably can apply a very simple idea like okay, because your PV is conserved, so it's constant. Okay, PV is conserved when you have adiabatic flow and when you have inviscid flow. Okay, so only thing you can generate PV is friction and or diabatic heating or cooling. Okay, and okay, so PV is constant. So PV constant, that's probably just is a very simple one, like shallow water. Then what we have will be zeta plus F divided by delta G. That will be equals to constant. Okay, so now when we have flow comes in, and then here we are stretching. That means we have this column stretching, and assume F is constant because it's airplane. We are dealing with the kind of mesoscale flow. Then only way to keep this constant is to have zeta increase. Okay, so in order to keep constant, zeta had to increase. So there, at upstream here, upslope here, then zeta, but zeta increase, okay, from zeta equals to 0. Upstream, right? Upstream, we assume zeta is equal to 0, no rotation. Okay, then that means at that point, zeta will be positive. Okay, that's why we say positive here. Okay, and then to here, we have delta G over the mountain peak. Okay, and that decreases. That means zeta had to decrease in order to keep the PV constant. Okay, and that means zeta had to be negative. Okay, so, and then here just, okay, same thing too. Okay, here you got stretching, then you got zeta greater than 0, and then return to the original height. Then zeta will become 0 again. Okay, so here we have a positive vorticity. What does that mean? We have positive vorticity. So if this is our mountain, this is our mountain. Okay, so flow come to here, and then we have positive vorticity here. What does that mean? Where is the flow going to go? This is positive vorticity. Okay, so this is mountain, right? So flow comes in to here, to here. You only have 3 ways. There's no other ways. Okay, come to here near the mountain. You only have 3 ways. One is keep going. Okay, same direction. And other way is turn to north. other way is turn to south. This is not the case, right? Because we have zeta become positive. So which one is positive? This one or this one? This is not going to be the case because this is 0, right? Straight line, vertical vorticity will be 0. What's this one? This one positive or negative? Positive, right? Because go this way, just use your right hand. Just use your right hand. Flow comes in, turn to north. Then vorticity will be this way. That will be out of board. Out of board is positive. Okay, because here we are talking about x direction and y direction like that. So out of board is positive. So if flow comes in, turn to north, and look at your thumb. Okay, your thumb. Okay, go this way. You turn this way, so go to out of board. That means positive. Okay, so this is positive vorticity, this is negative vorticity. So in that case, this is not the case. This is not the case. So flow will go to north and come back here like this. Okay, so over the mountain region, your sea flow go to north, go like this. So this is kind of anticyclonic flow. Anticyclonic flow like this. Anticyclonic flow. So over the mountain region, your anticyclonic flow. And other way to view this is, okay, when you have flow comes up, here become colder. Why? Expanding, okay, adiabatic expanding, become colder, so whole area become colder, and once you're colder, okay, it's going to create negative vorticity, right? Okay, when that's shrinking, you got negative vorticity. So you got this, okay, so then flow comes in, we'll turn to north, okay, and make a circle anticyclonic because, because it's colder, okay. And why colder become anticyclonic is like this. So say if we have so say you have one area, say even no mountain, okay. So this area is kind of cold. So your area is cold here, even no mountain, cold here. What's going to happen to the flow? Divergence out. So we're going to have, okay, divergence out like this. Okay, this is larger mesoscale mountain. So once you take a long time, like 6 hours, 12 hours or longer, then Coriolis force comes into play. So which direction is going to deflect the air? To the right, right? To the right. In northern hemisphere, of course, like this. So then you're going to have this flow. Like this. So that we acquire anticyclonic flow. So that's why over the mountain region you have colder air, and we call mountain high. Okay, mountain high pressure, mountain induced high pressure. Okay, that's why. So we have kind of colder air, we induce high pressure. The high pressure push air out, and that with Coriolis force, this is larger scale mountain, or larger mesoscale mountain. So then you got this, and you acquire anticyclonic flow. So that's why you have high pressure here, anticyclonic flow like that. Okay, and that has strong impact. Like later we are going to talk about it. Okay, but let me give you a kind of kind of heads up. Let me give a heads up, like so. So, for example, if you have Alps, okay, Alps like this, the European Alps, and if say we have, say a cold front coming in, because the mountain induced high pressure, okay, so we have pressure here, and high pressure gives us like this, and that will bring this eastern part of the, okay, of the cold front to here, faster than western part, and then eventually they come together, and then they generate a cyclone here, okay, and that happens to Taiwan too. Okay, when you have the front, like main front, come in, and then we see this part here. Okay, there are two regions in Taiwan's case. One is where mountain induced high pressure, so this push this way, and so you have the mountain induced high pressure. Okay, so this part go faster. Second part is we have southwesterly monsoon that will retard, okay, 阻挡, okay, make this slower, and this one faster because partly this high pressure, okay, so this go faster. So that happens in the kind of cold front, like the main front passing over Taiwan, kind of they split, and eastern flank go faster, okay, it's because of high pressure, and western part partially because of the high pressure, but partially also been added this southwesterly monsoon flow, okay, make the western flank of the front going slower. By the way, if we cannot finish this by Thursday, we still need makeup time, okay? It looks like it's going slower than what I thought, yeah. Okay, so I think probably we are done here. So I let you read details, okay? But I think a basic concepts I already passed to you. So this one is that solution we discussed, okay, for two-dimensional rotating flow passing over two-dimensional mountain ridge, okay, and then you plot it, and you can see like this, okay, and you can see for the rotating flow. Okay, rotating flow, and we still can see this upward propagating wave. Kind of difficult to control. Okay, we can still see this upward propagating wave. You see here, the first tilt upstream. Okay, but you also see this part. Okay, yeah. This is this part. This one is due to rotation effect. Okay, rotation effect. Some rotational effects on three-dimensional stratified airflow past and isolated mesoscale mountains are illustrated in figure 5.28. That's below. Like this. Okay. So here, if you have the long rotating flow coming in, and then its no-full number flow comes in, non-rotating, so F equals 0. Then you got a pair of D vortices, as we just started this morning. Now, if you add F, what's going to happen? Is these two will break up. So then you have one by one. This is negative vorticity, like this one positive vorticity, this one. They split, and then they start to go downstream. And this is called what? What kind of phenomena is this? Vortex shedding. Okay, that's von Karman vortex shedding. Okay, and why? It's because this is symmetric flow, symmetric of the flow being kind of broken, so it becomes asymmetric. Once you get asymmetric, then you start to get the vortex shedding. Okay, and sometimes it's difficult to kind of simulate this because you have to make everything symmetric, so then they stay symmetric. Otherwise, very easily you can get this kind of vortex shedding. And both of them are kind of low full number flow. Okay, the flow is very slow, or mountain is high, or certification is strong. Okay. So I think I already discussed about that. A southerly barrier jet forms along the upslope through geotrophic adjustment. In response to this reversed pressure gradient force in a rotating atmosphere. So here we are talking about 5.28a. So here, with rotation, you can see a barrier flow here, very strong barrier flow. Okay, for this one, you do see barrier flow, but not as strong as here. So just imagine this is Taiwan. Just imagine this is Taiwan. So flow comes in, and then this settle point shifted from center line to south. And then here you have very strong barrier jet. Okay, just imagine this is like Taiwan. When you have the southwesterly monsoon, okay, the southwesterly monsoon, and then split point here, and here barrier jet very strong here. Okay, yeah, that can help Taiwan's case too. Okay, vortex shedding we already discussed. Okay, barrier jet we discussed. Okay. In contrast, there's no barrier jet in non-rotating flow 5.28c. This one, no barrier jet here. But here we have barrier jet. It's partly is because of this rotating effect. Okay, rotational effect. Of course, partly also the southwesterly summer monsoon for Taiwan's case is coming from southwest, and that will add to the strengthening of the barrier jet. Okay, so in Taiwan's case, in northwest Taiwan, under this southwesterly monsoon season, okay, we have these rotating effects give us best barrier jet in compared to this non-rotating flow. And second reason is we also have the southwesterly monsoon that contribute to also strengthening that. Okay, so we have two reasons of that, of the barrier jet being produced over northwest of Taiwan. Okay, other thing is about the topographic Rossby waves, which occasionally you will hear people saying that, and also occasionally you will read papers talking about topographic Rossby waves. Okay, and to understand that, you also can consider like a barotropic atmosphere that is pushed up northward against the sloping of east-west oriented flow. So here we are considering like the west-east oriented mountain like this. Okay. Okay, and then we consider air parcel going to the north. Okay, and maybe we should stop and then discuss about this after we take a break. Oh, no, we stop at 4 o'clock, right? Or 3:50. Okay, so maybe we discuss tomorrow. Okay, tomorrow morning, right? I think this last lecture for today. Okay, yeah, So let's stop here and continue tomorrow. Yeah, okay, we'll do this and then we start to talk about one very interesting, also important subject, the psychogenesis. Okay, so a lot of exciting subject to talk about. Okay, I'm not 100% sure we can get done, okay, by Thursday, so we may still have the makeup lectures. Okay, yeah. Okay, great. Yeah, so you guys have, have a good evening and see you tomorrow.